Hello friends. So in vibrations, the pendulum play an important role. So we will today discuss some numericals based on pendulums or simple pendulums. So determining natural frequency of a pendulum is a regular question in most of the university question papers. Sometimes it comes as pendulum or sometimes it comes as a combination of pendulum and a spring system. So starting with a pendulum, so we will see how we can find the frequency of a pendulum. So natural frequency of pendulum, if you know how to find it for a pendulum, you already know how to find it for a spring. So if you can combine the two concepts, you can solve most of the problems. So finding natural frequency of a pendulum, the some parameters are required. One is L, that is length of pendulum string, and other one is mass of pendulum. And one more parameter required is theta, which is the angular displacement. So these are the parameters required. So this can be solved in many methods. The most easiest method is by equilibrium method. Equilibrium method. So equilibrium method is nothing but the total sum of all forces and moments acting on a system should be equal to zero. Or in case of angular motion, we can write equilibrium method as inertia torque must be equal to external torque. This is equilibrium method. So in linear motions and else we can apply it as total sum of all moment and forces equal to zero, and also it can be translated into inertia torque equal to external torque. So for a pendulum in this mean position, you can see this is the mean position of the pendulum. To move it to an angle theta, you should give an initial torque of I alpha, that is I is the moment of inertia, and this will be the direction of initial torque, and that will be equal to I times alpha. Alpha is nothing but the angular acceleration. We know force is equal to m into a in linear motions or linear motions. So m is equivalent to moment of inertia and alpha is equivalent to a. So ma is nothing but I alpha, Newton's law of motion. So that I alpha will be the inertia torque. So the external torque will be, that means the resisting torque that is acting on the system will be that in the opposite direction, because this pendulum will tend to come back to its mean position. That will be the direction of external torque. This will be the external torque. And this external torque we can find out by taking moment. So for that we need to understand what are the forces acting on the system. So at this position we know there will be a force acting in this direction, that will be nothing but the m into g due to its weight, self weight. And next one that will act is, because this is an angular position, so there will be a component forces acting, and that component forces will be, if that is theta, then this is also equal to theta. So this will be mg cos theta, horizontal component, and this will be mg sin theta. So these are the forces acting, and to find the external torque we can just equate these forces. So this will be I alpha, sorry, I alpha, and external torques will be in the opposite direction. So mg and the force that is acting along the direction of I alpha is mg sine theta, and mg sine theta into the perpendicular distance, that will be L, because torque is force times perpendicular distance, so that will be L mg sine theta into L. So these are the this can be called as the governing equation by which we will define the natural frequency. So we already know alpha is angular acceleration, and if theta is angular displacement, and then alpha can be written as d square theta by dt square, because acceleration is second derivative of displacement. So we writing it in the notation of I used in vibration, that is theta double dot. So I'm writing it as I theta double dot is equal to minus mg L sine theta, or we can write it as I theta double dot plus mg L sine theta is equal to 0. And for pendulums, we take theta as very small. That is an approximation we use to find out the natural frequency. So if theta is very small, then sine theta will be approximately equal to theta. So we can reduce this equation as I theta double dot plus mg. Okay, we have used small letter L, so I will just change that L everywhere into small letter L, or the lowercase l, to avoid confusion. That will be mgl. Yeah, L, that is the length of the string. So mgl into theta equal to 0. Or we can divide that I, and we can get mgl over I times theta equal to 0. And we know I is equal to m into L square, that is moment of inertia, ml square. So if you substitute that, we will get theta double dot plus mg L divided by ml square is equal to 0. And we can reduce that into theta double dot plus mg divided by, sorry, m and m will get cancelled. So what will be left is g by L. G divided by L theta is equal to 0. And we know for a simple harmonic motion, the equation is theta double dot plus omega square or omega n square times theta is equal to 0. So let this be equation number 2 and this be equation number 1. So comparing it with simple harmonic motion equation, we will get omega n square is equal to g by L, or omega n is equal to root of g by L. So natural frequency Fn will be equal to 1 by 2 pi omega, 1 by 2 pi times omega n, that will be 1 by 2 pi times root of g by L, which will be our natural frequency of a pendulum. This we might have studied in lower classes also. 1 by 2 pi times g by L. That means the frequency of the pendulum does not depend upon the length of the string, oh sorry, does not depend upon the mass of the pendulum. It only depends on the length of the spring. So this is how you find the natural frequency of a simple pendulum. We will continue with the more complicated problems, which are problems related to mass of the pendulum attached to a spring, or a string of the pendulum attached to a spring.